Good morning. Can you all hear me okay?
Yes, sir.
Okay, cool. Just for the time being, I'm going to mute everybody, but if you have a question, please don't hesitate to unmute yourself and ask the question, or ask a question. Because sometimes I hear background noise, so I just figured I better mute everyone. But don't hesitate to unmute yourself and ask a question. Okay, so I'm Professor Calabrese, and you're here for Physics 210. And so this Friday lecture is going to be a little bit, I think, a little bit difficult, just because we're here for 3 hours and 5 minutes. So for today, what I'm going to do is I'm going to lecture from 11 to 12:20. Take a 20-minute break, so can eat lunch or something. And then I'll finish my lecture from 12:40 to 2:05. How does that sound? Does it sound okay? Okay. Now, it's possible that later on this semester, what I might do is lecture the first half of the class and then provide a video maybe from my Wednesday lecture or my Monday lecture for you to watch. That way, you don't always have to sit here for 3 hours. Because I know 3 hours is a very long time to sit through a Zoom session. Okay, and if you have objections to, if I have a lot of people with objections to having you go watch a video, just let me know. I'll do the 3 hour lecture. Okay, but there's going to be times where I probably won't do the 3 hour lecture. Like today, I think it's important for me to do a 3 hour lecture because it's the first day. Okay. I need to make sure that I'm recording a lecture. So when I have the Zoom on, make sure and remind me that this thing is recording. For some reason, when I set up my meeting in Confer Zoom instead of the regular Zoom, I didn't have an option to set up recording for every meeting. But I'm going to see if I can go to Zoom and change that. In fact, what I do with my lectures, I actually record twice. I'm not only recording it on Zoom, but I have a video capture software, and you can see it because I'm sharing the screen of the video capture software. So I record it twice. And the reason why I do that is because sometimes the Zoom meetings, the signal's bad. And so when the signal's bad, the recording is bad too. But my video won't be. The only problem I have with my videos is sometimes I click on this window and the recording stops. Okay, so then I have to restart the video. And then I have to actually collect 2 files afterwards and merge them together so I can post it on YouTube. So I will post whatever I record on YouTube, and probably at the end of the week I will give you the URL for that. Okay. And if you've noticed, I emailed you guys the URL for the Physics 210R class. That's the problem-solving course associated with it. You guys don't have the option to take it. So I figured when I teach the Wednesday 210R class for my other 210 class, I would record it and send you a copy of it when I complete it, or a URL when I complete it. I should, by the way, I should let you know, it's possible that I might have to be interrupted during this lecture. I am expecting a home inspector to come into our house, and of course they give you an 8-hour time window, so I don't know when that person's going to come. So I might be interrupted for about 5 or 10 minutes, and if that happens, we'll have to take a 5 or 10 minute break, and I'll be back in 5 or 10 minutes. Okay. All right. WebAssign. Did you all sign into WebAssign? Now, let's be careful. When I created the WebAssign originally, really what I do is I created it for the Monday, Wednesday class, and then I copied the Monday, Wednesday class into this class. But when I created the Monday, Wednesday class, I copied everything from last semester, which is the same book as your Physics 205 class that you had. But I think what I did, there was a button that popped up that said update. I clicked update and it changed the textbook. And I couldn't change it back. And I contacted WebAssign. It's a week ago and I still haven't heard from them. So what I decided to do is I created a new WebAssign class. So I uploaded a second set of assignments. And all the assignments start like this. And then the only thing that changes is the homework number. We'll leave 9th edition, homework 1, 9th edition, homework 2. Those are the ones you want to do. Because these assignments are tied to the textbook you used last semester in Physics 205. And if you signed up for the multi-term use of the WebAssign, then you should not have to pay for anything this semester. I need you to complete the first homework assignment by next Friday. This is my only way to prove whether or not, really to prove whether or not you're really a no-show class, because the regular lectures are optional. The only way to see if you're actually involved in this class is to see if you do the homework. And so I need you to get this done by next Friday. If not, I'm going to have to drop you. If you've never even started, I'm going to drop you. Okay, I'm going to consider you a no-show. So please make sure you go into the WebAssign, look at the assignments on Canvas that start with 9th edition, homework 1, homework 2, etc. Those are the ones you want to use. And there's a video on Canvas that shows you how to use WebAssign. And if you have trouble with it, please let me know, because I'm running WebAssign a little bit different from the way you use it in 205. I've actually integrated it into Canvas. So what that means is that you go on the assignment, you click on it, you're automatically logged into WebAssign. Do not access the homework assignments from WebAssign. Access your homework assignments through Canvas. Okay, access your WebAssign through Canvas. Okay. All right. Any questions regarding the WebAssign or concerns? No questions or concerns? Okay. As a reminder, I do have student help hours Monday, Tuesday, and Thursday from 1 to 2. So I'll either be available on Zoom. I'm actually going to have two things open at the same time because of what students want. I'll actually be available both on Zoom, and I know a bunch of you folks like Discord. So I'll be available on both. Okay, so I'll have both open. It's going to be kind of strange how it's going to work, but I'll have them both open, and I can answer your questions at those times. And if you would like to set up an appointment with me at other times, please don't hesitate to ask me. You can always set up a Zoom appointment. Okay. Make sure that you watch the video that you saw, that's on the home page of the 210 Canvas site. Okay. Make sure you go through the Canvas site and get familiar with it. Okay. Most folks in this class will be familiar with Canvas because we migrated to it last semester. I want to say something about the exams that we'll be having this semester. The exams will be synchronous. The exam times and dates are posted in the syllabus. Okay. And I'm going to adhere to those dates. I'm not going to change it because of the difficulty students might have with scheduling. But I'm not going to change those dates for the exams, especially for this Friday class. Okay. And so on the days we have an exam, 2 of the 3 hours will be dedicated to the exam, and then the last hour will be dedicated to lecture. I still have to lecture because of the fact that we have a day later on the semester where we miss a 3-hour lecture. And that'll be Thanksgiving. And really, when you miss a 3-hour lecture, it's really like missing a week of class. Okay. So I need to, actually, before I get to Thanksgiving, I actually have to be ahead of my other class. Okay. These exams, there's 5 exams. The first 4 exams are your major ones. They're on the main units of the course. They're each going to be worth around 19% of your grade. And then the last exam, just to take the pressure off, is going to be worth only 9%. And the last exam will be on the last day that we meet. And on that day, we're just going to have a 2-hour exam, and that's it. Okay. So we'll miss that last hour. And most likely that last exam probably will take 2 hours, because the last exam will be on just one chapter called Relativity. And it's all going to depend on, how much is on the exam. It's going to depend on how much I cover on that topic. Okay. Now, you all got an email regarding the lab kits. You should have got an email yesterday. So please try to come out Monday or Tuesday. We already had our first lab on Monday, and I talked about the first experiment, the property of the charge lab. And you need to have something built by, you need to have the electrophorus built. Remember this guy that I showed you on Monday, and the electroscope built by September 4th. And you're going to create a video for me for the lab part of the course, and upload the video into Canvas. Okay, so you'll go to the assignment in Canvas for the lab, okay, and upload it into Canvas. All right, and remember, all you got to do is show that whatever you built works. So it's a video that's maybe a minute tops. Okay. Any questions regarding the lab kits? No questions, concerns? Okay. But no questions in general regarding this course. You saw the video on the home page. Did you have any questions regarding how I conduct this course or my expectations? And remember, if you have questions, make sure you unmute yourself. No questions or concern? Okay. One of the things I do in Physics 210R is I actually help students go through the homework assignment. And so your homework assignments are going to be the same as the homework assignment for my Monday, Wednesday class. So the problems I solved the other day for 210R will probably help you on this homework assignment. And then next Wednesday, I'll have another 210R, which will have questions on the same homework assignment. And so hopefully by the time you get on Friday, you'll have enough information to help you get to the assignments. I will use lab time for you guys to answer questions on the homework. As long as I have time in lab to answer questions on the homework, I will do so. Okay. All right. So we okay so far? I'm not really going through the syllabus here because of the fact that I posted that video online. Okay, and the other reason why, because you've been in the 200 series, you know what to expect. Okay, if this was Physics 105 or Physics A, a more beginning course, I would probably spend the whole class period talking about the syllabus. You guys, you folks all know how things go in the classes, so just make sure you read through the syllabus. Make sure you understand my course expectations. Okay, and please don't hesitate to ask questions because I'm here to help you learn the material. I mean, I'm going to challenge you in this course. but I'm also here to help you learn through. This first unit in this course is not going to be an easy unit. Okay, it's not going to be an easy unit. It's probably out of all the 205 through 10 through 15, this is probably the hardest unit you'll encounter. Okay. Just to let you know, so you there's no surprises. Okay, I mean, if you guys don't have any questions or concerns or anything, I'm going to start lecturing. Okay. So my objectives for today are Coulomb's law. I will discuss Coulomb's law, and I'll talk about the electric field. That's the other topic. And I'll spend a substantial amount of time describing the electric field and how we do some calculations involving the electric field. For two different important cases. This one's going to be non-calculus based. This one will be calculus based. And you'll see this unit is requires you to know your calculus. Okay. Or at least remember it. Okay. So this is the breakdown of our units this semester. So the units break down very nicely because they're basically 3 chapters apiece. The first unit that we're going to look at is we're basically going to be focusing on charges in equilibrium. The second unit, we're going to make the charges move. We'll talk about electrical conduction and circuits. The third unit is what are the effects of moving charges while they produce magnetic fields. So we'll talk about magnetic fields. And then the fourth unit is what happens if you have a time-varying electric field? What happens? What are the repercussions, or what are the consequences of having a time-varying magnetic field and a time-varying electric field? And then finally, we'll do relativity. So the first 4 units are your main units of this course, and so each one of the first 4 exams is worth 19% of your grade. The last one's worth 9. All right, so at first here I'm going to talk about Coulomb's law and electric charge, and then the topic on copiers, I'll talk about that on Monday on lab. Okay. And by the way, because we only meet twice a week, if you have questions regarding anything I said today, you can ask in the discussion board. Those of you who like Discord, you can ask in Discord. You can email me. I'll bring them up on Monday in lab. Okay. All right. So we said something about charge in the lab the other day. I want to say a few more things. The idea of charge was really known by the ancient Greeks around 600 BC. And then we started to learn how to charge by contact. We talked about that in the lab. And Gilbert really was able to learn how to distinguish between an electric force of attraction and a magnetic force of attraction. And then around 18th century, and really Franklin was responsible for this. And this is Benjamin Franklin, okay, one of the people who signed the Declaration of Independence. All right. He actually came up with the idea of plus and minus charges. And really he talked about it in terms of plus and minus electricity. And he introduced the idea of conservation of charge. Then around 1897, J.J. Thomson measured the charge to mass ratio of the electron. And a few years later, Millikan actually measured the charge of the electron, and then said charge is quantized. Okay. Okay, again, and we talked a little bit about this in lab the other day, but if I want to define what charge really is, Charge is like mass. But it's a property of matter I want to get the words exactly right. That causes a charged particle. You say this: a particle with this property to experience an attractive or a repulsive force. Now, it sounds kind of abstract. Okay. What if you compare it to mass? Well, in the case of mass, the property of matter, where a mass can experience only an attractive force. Here, you're dealing with an attractive or repulsive force. That's the difference. Just like mass charge is a scalar quantity, charge is conserved just like mass, and charge is quantized. And the unit of charge, Q, sometimes written with the letter E, is 1.602. And I'm not writing it on the digits, okay? Is this value. And this is the basic unit of charge. And the C is the Coulomb. So I'm not telling you the entire truth. Really, this is not the most basic unit of charge because I'm ignoring the idea of quarks. So the elementary charges are those of a proton, the electron, and then neutron, zero charge. Okay. There are quarks. The proton's made up of 3 quarks. The neutron's made up of 3 quarks. The electron's made up of 2 quarks. But let's not worry about that in this course. Okay, we're going to live in a world where the elementary charge is this, and the elementary particles are the proton, the electron, and the neutron. And then we'll learn about the photon too, which is a quanta of light. Those are the only elementary particles we're going to assume in this course. Of course, when you take modern physics, which is in the last part of your book, you'll learn about all the interesting elementary particles that are out there. Okay, but we won't deal with that here. So, like charges, they repel. Unlike charges, attract. And charges add algebraically. So if you have a charge, it's minus 2 times this number, and you add it to 2 times the positive version of this number, you get 0. So if you have a helium atom, which has 2 protons and 2 electrons, let's go. This has 2 plus charges. This has 2 minus charges. You sum them, you get 0. Or I can write like this. And that's a neutral atom. Okay. And you get weird behavior. For example, if you take two electrons, let me rephrase that. If you take an electron and its antiparticle, really, my mistake, I should word it. I should write this down. That's a proton. Okay. If you take an electron and its antiparticle, which is called a positron, and you slam them into each other at a high enough energy, guess what can happen? So you get one electron going this way, and a positron going this way. You slam them into each other, they collide, and guess what happens? We get two photons. They have to be going fast enough for this to happen, okay? And we won't talk about how fast here. So this is an electron, and this is a positron. And I gotta say, I guess, what a positron is. A positron is an electron with the opposite charge. It's the antiparticle. So this is an antiparticle. They have the same mass, because mass can only be positive. But this is the antiparticle to this thing. When you slam them into each other, the mass disappears, but the mass gets converted to energy. The famous equation E equals mc squared. Mass is a form of energy. Okay? So you might say, well, mass isn't conserved. Well, if you say mass is a form of energy, it is. Okay? So energy is conserved in this collision. And so is charge, because when they initially during this collision at zero charge, and when you produce two photons, two quanta of light don't have charge. You'll be able to conserve energy, you'll be able to conserve linear momentum, you will be able to conserve angular momentum, and you'll be able to conserve charge in this collision. You will not violate any laws of physics. What's even more interesting is if you can take two photons of sufficient energy and you slam them into each other, the light can be converted into mass. And you will get an electron and positron pair. It's called pair production. Okay, the first one I talked about is called pair annihilation. The second one is called pair production. Again, you're conserving energy, charge, linear momentum, and angular momentum. Because you need to do this in a fairly sophisticated laboratory environment. Okay. But this gives you an idea what properties of charge are. So we said that charges exert attractive or repulsive forces on each other, but what is the equation that represents the force between two charges? Well, it's determined by Coulomb's law. Coulomb devised an experiment to measure the force between two charged particles. And I was able to show that the force between two charged particles depends on the product of the two charges. And so what you see on the screen is an equation that represents the magnitude of the force between two charged particles. So let me write this down. So F is the magnitude of the force between two charged particles. Well, let me be more precise. If I'm writing the magnitude of the force, then I got to make sure that these two are absolute values because the Q's can be positive or negative. Let's say I have a charge Q1 here and a charge Q2 here, and I call this F12, which is the force on 1 due to 2. The force on charge 1 due to charge 2. Obviously, you know, the direction of the force will be along the line joining them. So they're going to be repulsive or attractive. Now the K is a proportionality constant that really links the force to these quantities. Notice this equation. You guys took Physics 205. This equation looks just like the law of gravitation. In fact, mathematical form is exactly the same. And when you had 205, you did a lot of calculations involving this equation. So, because of the fact that this has the same mathematical form as this guy, the way you're going to be doing the calculations in this class will be the same as what you did in Physics 205. Because of the fact that the form of the equation is exactly the same. The only thing that's different is the letters. Here you have n's, there you have q's. Here you have r squared, and the r, remember, is the distance between the two objects. The center to center distance between the two objects. And then these are the constants. Now remember, g, the gravitation constant was 6.67 times 10 to the minus 11 Newton meter squared per kilogram squared. K, we need a different color, is 8.99 times 10 to the 9 Newton meter squared per kilogram squared. That's Coulomb constant. Sometimes I'll just write it as 9 times 10 to the 9. And let me know if you can't see something very clearly, okay? Please don't hesitate to interrupt me. What do you notice between this number and this number? It's a reflection of how strong the two forces are. Oops. Let me go back. All right. You see that this number is huge compared to this number. So the force of gravity is way smaller than the electric force. If I write F sub B as the electric force, the magnitude of the electric force is way bigger than the magnitude of the gravitational force. And I'll do an example in a little bit to give you an idea of the difference. If you want to investigate the electrons in an atom, in other words, how is an atom stable? Where are the electrons in the atom? What is the energy of the electrons in the atom? If you do a theoretical calculation, you basically ignore the gravitational forces between the electrons. And look at the size of this constant and the size of this constant. They differ by a factor of 10 to 20. Okay? So there's a huge difference between these forces. In fact, I'll do the calculation and show you how insignificant this force is relative to this force. So when we're dealing with large planets, yeah, this becomes relevant because the masses are large. When we're dealing with small objects, this force is very insignificant compared to this force. check. Did I mess up? Oh, yes. Thank you. I don't know if you noticed when I was writing this one, I started putting Coulomb squared here. And then I changed it to kilogram. And then when I did that one, I did the wrong thing. So thank you. Okay, thank you for pointing that out. Sometimes I don't see the chat right away. Okay, sorry. But thanks for pointing it out. Yeah, you're right. This is Newton and meter squared per Coulomb squared. Okay. Now I want to say something else about Coulomb's law. Just like Newton's laws, Coulomb's law is not always valid. Coulomb's law really only works if the particles aren't moving. If these two are stationary, this works. And if you can treat the objects as point charges, this works. Which means that if the objects have spherical symmetry, you can use this equation. Okay. And if they're not moving, too. If they're moving, you can't use this equation. Why? Why is it that if they're moving, you can't really use this equation? Well, if this charge starts moving in, let's say this charge is moving towards Q1, we'll find later on in the semester that moving charges will generate a magnetic field. And that the magnetic field can produce a charge on this one because when these two objects are near each other, this is not going to be stationary, it's going to move into it. So you're going to have electric force and magnetic force at the same time. And it's time varying. If you have a time-varying magnetic force, it will actually induce an electric field. We'll learn that in chapter 31. So you get very complicated, something that's very complicated that happens when these two move toward each other, which cannot be explained in terms of Coulomb's law. Okay. In fact, you could have a situation where you put a charge in space, there's no charges near it, and it will experience a force. Because it's in a region where there is a time-varying magnetic field which creates an electric field. So you can actually have a force on a charged particle in the absence of force. So in other words, if I make it zero, Coulomb will always say this is zero, even though Q1 will experience a force. We will introduce another concept today, which always works, which is called the electric field. Okay, the Coulomb's law doesn't always work. That's one thing to read. I mean, Newton's laws don't always work either.
Why doesn't it always work?
Well, if the charges are moving, then you're going to also have, well, moving charges produce magnetic fields, and if you have moving charges in a magnetic field, then that produces a force too.
Oh, okay, I see.
And then you have a time-varying magnetic field, which creates another electric field. It's a relativistic effect. Luckily, that effect is small, as long as the velocity of the particles is much, much less than the speed of light. We can ignore those effects. Okay, as long as this object is moving at less than 1% of the speed of light, we can probably ignore those effects. But because particles are light, we can get small particles to go really fast. You can get small particles to go close to the speed of light. Okay. So that's why we got to be careful. We have to explain that this is not always valid. Newton's laws are not always valid either, right? Remember, Newton's second law is not valid in a frameless accelerator. So this slide kind of reiterates kind of what I've been saying. Coulomb's law is only valid for stationary point particles, or in cases where the object acts like a point particle, meaning something with spherical symmetry. Now, one of the ways an object can act like a point particle is when its dimensions are much less than their separation. So, for example, let's say I have some weird shaped object here. Its dimensions are 10 centimeters. And let's say I have another weird shaped object here. And its dimensions are also 10 centimeters. But this distance is 10 meters. Okay, now if they're 10 meters apart, probably these small objects will look like point particles. And so yeah, I can use Coulomb's law. Okay. Again, Coulomb's law cannot explain the case when the charge experiences an electric force in the absence of other charges, which you will see happens in chapter 31 later on in the semester. You can actually induce fields which will produce forces on charges. Coulomb's law cannot explain that. Okay. Now, I talked to you about Coulomb's constant. I want to say another way one can write this equation. A lot of times you'll see this equation written in terms of the following. And this is called the permittivity of free space. If you solve for epsilon naught, what you'll get is 8.85 times 10 to the minus 12. And these units reversed. And in fact, when we were on Quran, we would do an experiment where we actually measure this number. It's a teeny tiny number, but you'd be surprised you can measure that number pretty accurately. Okay, that's called a permittivity. Of free space. Okay. Hold on just 1 second here. I gotta turn off the sound on my phone so it can go off. Okay. All right. What does this thing represent? And we'll talk about this when we get to chapter 26. But this thing represents how well the field lines. We'll talk about the field. Penetrate a material. I mean, right now, this represents the values in a vacuum. Between now and chapter 26, we're going to be talking about everything in a vacuum. About what happens when you have a real media made up of atoms. What is the effect? Well, this number changes. And if you have media that's very nicely behaved, basically what happens is the new value for the permittivity is this number times a constant. Okay, it'll just be this times a constant for various media that behave nicely. And what that represents is how well the field lines will penetrate a material. So for example, for a metal, a conductor, the field lines will not penetrate the material. The cap is big. I'm sorry, epsilon's big. Make sense? And there's an analogous one to this when we do magnetic fields. So what I want to do is I want to give you feeling for the relative size between the electric force and the gravitational force. So I want to consider the force between two electrons. You can just say, okay, they're a meter away. Where does that give us? What is the force between two electrons that are about a meter away? or I'm sorry, a meter apart from each other. So this will be actually a pretty straightforward calculation. I have one electron here, another electron here. This is 1 meter. And really, the distance is not going to matter because both equations have an r squared in it. I want to know the ratio of this force to that force. I want to know that ratio. Well, first of all, the charge on each one of these is negative. And the mass of the electron actually, I made a mistake earlier. I said that Millikan measured the charge of the electron. He measured the mass of the electron. Okay. And from that, then you get the charge of the electron. Anyway. So now that we know this information, let's calculate the ratio of F sub G over F sub E. I'm going to take this equation. Since the masses are the same, M1 times M2 is basically M squared. And the Q1 times Q2 is basically Q squared. So, let's put the numbers in. What we get. And I'm going to apologize ahead of time. I'm not going to always write the units in because my board is small. I want to run out of space. Okay. You can see that the numbers in the numerator are small, the numbers in the denominator are big. And this comes out to approximately that value. I'll show you how small the gravitational force is compared to the electric force. It's a huge difference. I want to show you a way now we can express Coulomb's law as a vector. So let's say I have two charges. I'll change colors. Let's charge Q1. Let's charge Q2. And when I write it as a vector, I can write it like this. The force is equal to K, Q1, Q2, over R squared, R hat. Notice I did not put in the absolute values in that equation because I'm actually I'm actually writing the equation for the vector. In order for this to be consistent, I got to define what R is. If I am looking at the force on object 1 due to 2, then the unit vector is defined as the vector that points from the source that's producing the force on this guy to this guy. So it's basically, we'll say it this way. The unit vector is a vector that points from the source of the force to the test charge. The object in question is called a test charge. This is the source. If I were to look at the force on 2 due to 1, then my unit vector would start here and be directed towards this guy. Remember what a unit vector is, right? Unit vector only tells you a direction. And how do you write a unit vector? If I wanted to write a unit vector in IJ notation, well, just remember the unit circle. And maybe you can think about it this way. Students have a hard time with writing a unit vector. So this is a unit circle. And you know trig, let's say trig, you did some calculations with the unit circle, and if you wanted to know the coordinates of this point, okay, of the unit circle, basically those are the components of your unit vector. If you were at this point on the circle and you knew the coordinates of this point on the unit circle, then what you know is the x and y components of your unit vector. It's a vector of length 1 designed to tell you direction. Right? You can always describe a direction in terms of an angle, but you can write it in terms of a vector. So if I write it this way, if I call f theta, then my unit vector would be minus cosine theta I hat plus sine of theta j hat. Does that make sense? Yes, no? Okay, so hey, if you're having trouble understanding, please stop me. And later on, when I'm going to do this again, I'll talk a little bit more. I'll give you a more specific example how we determine the unit vector. So, in order to use this equation, I have to write an equation for the unit vector. I put in Q1 and Q2, and I just have to know this distance. In fact, the unit vector is basically the vector r, which goes from here to here, divided by its length. That's another way to write it. I like to see it this way. It's more, it physically tells me what it means. Now, when we do problems where we calculate force with Coulomb's law, I'm really going to not do this method for calculating forces involving Coulomb's law. And the reason why is because this is really not a physical way of doing it. And there's no intuition in it. Now, I created a video. It's a short 8-minute video, and I give you a link to it, where I actually use this method to calculate forces, where I actually write down what r hat is for a set of vectors, for a set of charges. And I said in the video, this is not the best way to do Coulomb's law problems. It's not physical. And the reason why I show you that because we're going to be using this r hat in other situations. We're going to use it a lot. So I want you to get used to it. So I did have a video, or I do have a video where I solved a problem about Coulomb's law. Okay, using this method. Now, Coulomb's law obeys the principles of superposition. There's a video in 210R. No, actually a separate video. If you look at the discussion board, the video for the problem using method 2, it's on the discussion board for our class. Okay. Yeah, anytime I make, by the way, that's a good question. Anytime I make videos of solved problems, I'll put them on the discussion board for that unit. Okay. Coulomb's law, it obeys the principle of superposition because the force acting on a charge is the vector sum of the forces acting on it. So let me just explain what that means. Suppose I have three charges in a triangular configuration, let's say. Okay, the three charges. And we'll call this Q1, Q2, and Q3. And I want to know the force on that object. The total force on that object is equal to the force between these two objects plus the force between these two objects. So it's the force between Q3 and Q1 plus the force between Q3 and Q2. I add. So that's what linear combination is. I can just add the force. I can just add a number. This is what you did in 205 when you added forces. What you did was you took linear combination of forces. When things obey the principle of superposition, the math becomes doable. When they don't behave the principle of superposition, the math becomes difficult. Now, another thing to realize is if I consider the force between these two objects, it's independent of this one. If I consider the force between 3 and 2, it's independent of this one. The sum, though, depends on, the sum of the forces depend on each other, but the actual individual forces does not. Okay, so you will see the principle of superposition in this course. You will see it in, you saw it in 205, although we probably didn't talk about it, and you'll see it in 215. And in 215, you'll use it a lot. So what I want to do is show you how to solve a problem like this. And I'll do an example. The first way, there's two methods. And I'm going to use method 1. Method 2 is in the video I just talked about. In fact, method 1, I created a video of method 1 too. Okay, so if you go to the discussion board, I have a video for method 1 and a video for method 2. So this example, you'll see it again. And the reason why I made a video is because for my Monday class, I didn't get to it, so I told them I'd make a video. Okay. First thing you want to do, this is a physical way to do it, is to draw a free body diagram. Okay. When you hear the word force, and you've heard this in 205, the first thing that should come into your head is a free body diagram to analyze the system. See, when I wrote the equation for the magnitude of the force between two charged particles, this equation represents the magnitude. There's no direction in it. In order for me to get the direction of the force, I have to draw a free body diagram. If I write it this way. Now, if I'm able to figure out the unit vectors between the charges, then I will use this equation and sum forces between each pair. I will sum the vectors between each pair and get an answer. And this is method 2, and I'm not going to do the example of method 2 here. If you're interested, you can watch the video. I'm more interested in you being able to do the problem this way. So I'm going to focus on this method. So you'll draw a free body diagram. Now, be careful. This is a mistake people make. If I'm interested in the force on this object, I only draw the forces of that object. I don't care about these two. I know that these forces, these objects experience a force, but we're not talking about this one, and we're not talking about this one. We're focusing on this one. So only draw the free body diagram on this object. That's what you do in Physics 205. All right? If you're given a cart being pulled by a string, you only draw the forces on the cart because you want to know the acceleration of the cart. You don't draw the forces on the string. Even though the string is part of the system. You do the same thing here. You have three charges. Yeah, you know these guys experience forces, but I'm only interested in the top object. So I only draw the forces on the top object. Okay. Then once I have my free body diagram, then I use this equation to find the magnitude of the force between these two and between these two. Then I can break the forces up into their x and y components. I can add up all the x components, and then I can add up all the y components. And once I've done that, then I can use the Pythagorean theorem to find the magnitude of the force. And finally, inverse tangent function to determine the direction of the force. I can also write my resultant IJ notation. So let's do an example. And I'm going to, method 2, like I said, is basically uses this method. So if you watch the video, method 2 will discuss this. So here's a simple problem involving three charges and an equilateral triangle. I want to find the force on the 7 microcoulomb charge at the top of the triangle. By the way, let me write down some unit conversion. And of course, these are in your book, but 1 microcoulomb is 10 to the minus 6 coulomb. 1 nanocoulomb 10 to the minus 9 coulomb. Right? Micro means 10 to the minus 6, nano means 10 to the minus 9. And 1, just in case, picocoulomb is 10 to the minus 12 coulombs. Okay? So let me redraw the picture here. I don't have a lot of board space, but we'll manage. So if you can't see something, please let me know. So what I'm going to draw is supposed to be an equilateral triangle. It might not look like an equilateral triangle. And I'm going to number the charges. 1, 2, 3. So there's my configuration. The distance between each pair of charges is 0.5 meters. And that's a pretty big distance. And we're assuming the system is completely isolated from the rest of the universe. And they're not moving. So I need to draw a free body diagram on the object in question. So I want to draw a free body diagram on the object up here. So I know that these two forces interact with each other. So I'm sorry, these two particles interact with each other. Since both of these particles are positively charged, that means that the 7 microcoulomb charge will be repelled from the 2 microcoulomb charge, meaning that this object wants to move away. Now, what about this one? and this one. Well, this is negative, this is positive, the force is attractive, and so, now let me label these forces. This represents the force on 3 due to 1. This guy represents the force on 3 due to 2. And let me resolve the free body diagram, even though I don't know the values that I'm going to put in there yet, but let me just resolve it. And let's see if I have another marker here. Let me do this. Let me draw these lines. My dotted line and my triangle. And since this is given as an equilateral triangle, all the sides are equal, I think you remember that all the angles are 60 degrees. Well, if that's the case, if I resolve these into 2 components, then those angles are 60 degrees too. In fact, let me do this. Let me write F31 sine of 60 minus F32 sine of 60. These 2 point to the right, they're both positive. Oops. I've resolved all my forces. It was kind of, sorry, everything's close together, that board's not that big. So the next thing for me to do is to calculate F31 and F32, the magnitude. Remember, the equation looks like this. So I'm going to put in the values. Now I'm going to do something different. I don't like writing a lot of stuff in scientific notation. It's too much writing. It's going to take me too much board space. So watch what I'm going to do. I'm going to write the Coulomb constant. And so Q1 is 2 microcoulomb. Q2 is 7. But I'm going to write it this way. Right, because each one of these is a microcoulomb. So a microcoulomb times a microcoulomb is 1 microcoulomb squared, or 10 to the minus 12 coulomb squared. So that's what I put here. Okay, that way I don't have to write, I'm saving space here. And so if you do this on your calculator, you should get 0.504. No, I do the other one. And some of you folks can see it already that this number is going to be double. Again, I'm putting the magnitude of the charge in here. So I get that. So now I have the forces resolved. I know how to write my x and y components, and I know the magnitudes. Then the rest is pretty easy because you guys didn't know how to do this already. I'm going to write F31, and I'm going to write it in IJ notation just for fun. Okay, so F31 is going to be 0.504 times the cosine of 60. Okay, plus 0.504 and F32 is going to be 1.008 times cosine of 60. And this one's going to be negative because it points down. I just add it. Or in fact, if you want me to write the values down, I'll do that too. Normally I don't do this part, but so this cosine of 60 is a half. Hold on a second. The cosine of 60 is a half. So half of this number is and then this one I don't have. Let me get my calculator. Then the bottom one and then when I add them, I get the following. So this is my force. That's the sum of the forces. And then I take the Pythagorean theorem to find the magnitude. And when you do that, you get 0.873 newtons. Everything okay so far? Okay. I got a couple more minutes, so now all I got to do is get the angle. All I got to do now is get the angle. So the angle, I just use the inverse tangent function. Of the y component. The y component is negative 0.436. I'm not putting in the units because the units will cancel in this calculation. And that'll give me minus 30 degrees. By the way, and I apologize ahead of time for this, sometimes I make my dots, my periods too small. So if that bothers you, please stop me. Okay? I make these too small sometimes. But it's hard to see. It's even worse when you're doing a chalkboard. Let's see. Yeah, this one's small. So it's 300, it's minus 30 degrees or 330 degrees. When you write these angles, please specify how you measure the angle. This is minus 30 degrees with respect to the x-axis. Or I can say 30 degrees south of east, or 60 degrees east of south. Okay, specify how that angle is measured. Remember I said this is how you do these kind of problems. If there were 4 charges, well, then there would be 3 terms in each line. Right? If you had 4 charges and you wanted to find the force on one of the charges due to the other 3, then you would have 3 terms here, 3 terms here. It's the same process, you just have more terms in your equation. Does that all make sense? Okay. Suppose that this was the following. Suppose I had this, please. Okay, suppose I had that case. When you encounter a problem like this and you have something like an equilateral triangle, you should take advantage of symmetry. Let me erase all this stuff. Let me erase this one. Okay. If they're both the same charge, you might not need to go through all this, but you probably need to make some arguments, let's say in an exam, that can simplify the problem. Don't just use the one, just don't say, oh, this problem has symmetry, this is the answer, but explain why. So, if these two are the same charge, then it's true then that the 7 microcoulomb charge will repel this one, and so we'll have another arrow that points like that. Now remember, this is an equilateral triangle. These 2 pairs of charges are the same as these 2 pairs of charges, and the distances are the same. So the magnitudes for the 2 forces are the same, and then we have the same angles. Now, if I resolve these 2 forces into x and y components, since the magnitudes are the same and the angles are the same, that means that these x components are the same. You can say that the x components cancel, since the magnitudes of each pair of forces are the same. And the angles are the same. I'm running it real fast, sorry. Okay? And then you can tell that the total force on the 7 microcoulomb charge is twice the y component of one pair. So basically, I would say the total force is 2 times f sub y for one of them. And so I would write 2 times k times 2 times 7 times 10 to the minus 12. And I'm running out of space. Times the sine of 60, which I'm missing here. That's my answer, I'm done. It's way less work than going through this. So if I notice symmetry in a problem, take advantage of it. But, say something. I mean, look at how much less work I did in this problem, in this case when I had symmetry. Take advantage of the fact you have symmetry. Yeah, it's similar to some of this what I'm doing is similar to the homework. Okay, So I think right now it's 12:21. Let's take a 20-minute break. Okay, so I'm going to pause my recording real quick. Let's take a 20-minute break.